I'm going to be talking about sums and sigma notation. Before we understand definite integrals, it's important to look at sums. Suppose that we have some collection of numbers that we want to add up, such as 1 plus 2 plus 3 plus 4 plus up to, say, 50. A useful shorthand way to write this sum without using ... is to say sigma. On the bottom we have I equals 1, and on the top we have 50 of I. What this notation means is that we're summing the quantity I starting from I equals 1 and going up along the integers until it reaches 50. In general, if we have any sequence, say a denoted by a sub I, indexed from 1 through n, we can write their sum as sum I equals 1 to n of a sub I, not a sub n. And this is equal to a1 plus a2 plus ... plus all the way up to a sub n. Let's look at several explicit examples of sums. Say that we have the sum from I equals 1 to n of c for some constant c. This is just equal to c plus plus ... plus c, where we have n copies of c. So this is exactly the same as saying n times c. So this sum evaluates to n times c. Another interesting sum to look at is the sum I equals 1 to n of I, like we said before. If we write this out, then this is 1 plus 2 plus ... plus the quantity n minus 1, and then plus n. We can actually use a pretty cool trick to add these numbers up by rewriting their order. We can write this as 1 plus n, let's group these together, plus 2 plus n minus 1, and then plus 3 plus n minus 2, etc. Notice that each of these pairs of terms adds up to n plus 1, so really we just have several copies of n plus 1. And since we know that there's exactly n terms that we're adding up in total, the number of these copies of n plus 1 must be n over 2. So this is equal to n over 2 times n plus 1, or n times n plus 1 over 2. Now in the case that there's an odd number n, the middle term of the sum will not be paired up with another term. However, since it's exactly in the middle, it'll still count for 1/2 of n plus 1. So the formula for the sum still applies. Another sum is the sum I equals 1 to n of I squared. This sum is equal to n times n plus 1 times 2n plus 1 all over 6. So this is the sum of the squares of the first n positive integers. Now proving this sum takes on this value is trickier and requires using induction. That is, we prove that it's true for n equals 1, and then assuming that it's true for n equals some value k, we prove it's true for k plus 1. So then 1 implies it's true for 2, and 2 implies it's true for 3, etc., so it must be true for all values of n. Another rule we have for sums is that given the sum I equals 1 to n of some constant c times a sub I plus some constant d times b sub I is equal to c times the sum I equals 1 to n of a sub I plus d times the sum I equals 1 to n of b sub I. That is, we can pull multiplicative constants outside of a sum, and we can also separate two sequences into two separate sums. This can easily be proven by applying the distributive property and commutativity of addition many times.